I tried it several times now. So, please.
Thank you.
Of it. And the aim actually is to be able to ensure an adequate geographical coverage to enable secure communication between public assets using, in this first stage, QKD as a technology. And for this reason, the European Commission has launched recently a procurement call to conduct a study on the system architecture for such infrastructure. And the idea behind this call is to have, as an outcome, a series of options for possible architectures that can actually serve the needs of the user requirements in three particular different kinds of select user studies. One is governmental communication, the other one is critical infrastructure, and also data centers. We had to be aware also that this is not the only source of information that need to be taken into account when shaping this initiative. The European Commission is already investing not only through the Quantum Flagship, but also through other parts of the Horizon 2020 program, some projects that are actually tackling very relevant issues in relation with the deployment of this technology. Some of the projects are actually developing or improving individual components. Some others are opening the possibility of having the QKD different approaches being tested in different test beds, and also we envision to have the layout of what will be the future internet based on the technology of quantum repeaters. So this is where we stand. So this is what we know from what is going on. And then the idea now is to get your thoughts about this particular topic and to actually initiate a discussion. I would like you to challenge you with to look at this from three different angles. The first angle is how far are we actually to be able to deploy this in a real world setting. And then if you think about that, there will be many questions that you can think of from the different protocols, how scalable they are for network configuration, how compatible the technology is with the current existing telecommunication technologies, but also the existing infrastructures, issues as certification, standardization, and so on and so forth. Another question that might be of relevance is Europe self-reliant in this field? Can we provide all the components of the technology that is going to be needed in such an infrastructure? And if this is not the case, are we going to do something in this respect, or are we going to rely in technology that is being developed outside the EU 27? That's another matter of discussion. And maybe last but not least, we are going to do a strong investment in deploying this infrastructure. So maybe it's good that we actually think about how upgradable this is going to be and how to ensure accommodate future technologies. And with these three questions, I just leave you for discussion.
Thank you for introducing this topic, David. Any spontaneous questions already? People have ideas or thoughts. The reason why I'm on the floor is that I'm going to push my mic and ask people on the spot. So let me start here. What do you think is the most important question to be answered from these three? One rule? Okay, one rule, I will keep the mic. And the second, please tell who you are and what's your affiliation.
Okay, I am Atilla Sakioğlu from Turkey, TÜBİTAK. I think I still don't know whether the technology is ready for the real deployment, I guess.
It's the most important question, whether the technology is ready for deployment. Now I'm going to find someone who's going to answer that question. Let me have a look. Sir, do you think that the technology is ready?
So, I'm Matti Partanen from Walter Meissner Institute. So, yeah, it's hard to tell whether the technology is ready, but yeah. Yeah, maybe we have to really focus on that and to get it ready. Maybe it's not yet there.
And from your professional background, are you working with this technology, or is this not really the quantum technology you're working on? Are you working on quantum technology for quantum communication?
Yes, I'm working on superconducting circuits and how to use that for quantum communication.
And any thoughts on what is needed to bring the technology you're working on to the level that can be applied?
So there are still some technological obstacles, so we have to make it more so that it actually real benefit of using the quantum technology compared to the classical one, so that it's actually useful.
Okay, thank you. Who else is working on the quantum communication technology? Oh, I'm here. Sorry. Yes. Could you pick?
Hello, Andreas Poppe. At the moment at Harvey Technologies Düsseldorf, I'm one of the elephants here, the few one. I'm working on quantum communication technology. I think that Harvey developed in Europe a really nice QKD system, very similar to Idiquantique and Toshiba, but of course it's not treated as a European system because many large fraction of our money is coming from China, and therefore the time gets harder and harder. We aimed really to get a European contribution, but somehow we failed. This is a kind of decision now of the US and the EU, of course. This is one point I want to mention. The second point, of course, is the applications are really not well defined yet. I asked Mr. Wiesmüller, who was on the podium yesterday from Austria, can you give me an indication how many links are used for Austria to connect all the different ministries, what is the rate and so on, and he needed to admit, I have no idea about it, but we will think about it. So therefore, this initiative is really highly needed to find where the use cases, in which direction to go.
Okay, thank you. On the back, there is a question. Yeah, thank you.
Hello, Simon Benjamin from Oxford. So I'm with one of the UK's big quantum hubs. It's not the communication hub. Suddenly it's all gone dark. Is that because I'm
There's
from
the
the
Brexit,
UK?
I think.
Yeah, that's right. It's like, everybody turn away. No, right. So a couple of quick thoughts which come from my interaction with the communications hub. I don't know if anyone's here from that, so perhaps I can speak for them. One of the concerns I have is it's not always obvious what this is a solution to on a societal level. So for the quantum computing side of things, it's clear, why we want them, or at least things can be said. It's not clear what a world in which there is quantum secure comms looks like, and whether it's a better or a worse world than the world we live in. So I think, and hopefully a better one, but I think that side of things really needs to be explained and promoted more. And it's not non-trivial, right? Because things like whether or not there should be ways for law enforcement to access communication channels are huge controversies. And it's not clear where quantum comms sits on that. And I've certainly talked to decision makers who've asked me about that, and I say, well, I can't speak for the community. So I think that element is missing. And certainly the technology is also not ready, but that's another side.
Thank you. Yeah, I think summarizing both comments, it's really about the use cases and the boundary conditions of this new technology, and therefore from an engineering perspective it's key to have these in place. Otherwise you cannot specify the requirements of what the infrastructure should look like. So let me see. The second question is about the European technology, European Union to be self-reliant. Just have a look here. Sir, can you make a statement? What do you think? Should Europe be self-reliant?
Well, I'm not an expert in quantum communication at all. I'm not involved in communication, but as a European, I would say yes.
Could you elaborate why?
Because communication has a lot of implications for security, but also for the citizens' well-being and security as well, so at an individual level.
Okay, to guarantee your civil rights, basically, in that sense. Okay, thank you. Okay, any other thoughts? So let me ask to the audience who's actually working on quantum communication technology here. No one dares to raise their hands. Only 2 people? Oh, this will be a tough job. Oh, Rob. Rob has always a good opinion. Could you, sorry. Oh, sorry, yes. Please, go ahead, and then I will get to Rob.
Yeah, so Klaus Jöns from KTH Stockholm, and we just started a collaboration with Ericsson to make a fiber link, sending single photons of some distance. And we actually used deployed fibers, and we had really big troubles. And I wonder if people think about how we actually want to do this, because there's a lot of background crosstalk from lasers if you want to use a quantum channel in a deployed network.
That's a fair question. I'm looking. Nick, can you answer or comment on that? Or rather not? Okay. Going to Rob. So, Rob, could you maybe elaborate a bit on the last question? How to keep attention that the future technology developments will still be able to be used if we start building an infrastructure now?
Hi, I'm Rob Thew from the University of Geneva still. Yeah, I mean, this is a hard question, maybe one we can interpret many ways, but I would say that with any technology, it's not like you develop a final product and that's it, and you all go home and just keep selling that product forever. I think this is one of the key roles, certainly with the flagship as well. We have the technology which, coming back to the first point, I think the technology is there, it is ready to be deployed. Obviously, it still needs to be improved, and that's where these new technological developments, whether it's in applied QKD systems for making the systems that we currently have better, or whether it's going to these entanglement-based quantum repeater type scenarios. And I think the idea is that we build on the telecommunication network that exists and all the infrastructure that's there with what we have, and we progressively make this better and more functional in the future.
Thank you. There is a comment over there, please.
I'm Richard Hughes-Jones from the Géant Association. We procured and designed the international network that carries the academic traffic around Europe and globally. And we have made some tests with quantum key transmissions, and we would be very, very pleased to support the projects that you're talking about. And in addition, I would like to take this opportunity to meet some of the collaborations and see how and where the likely sites are, so that we could get an estimate of the impact and cost it might be to make the tests you're talking about on the ground segments.
That's interesting. I think indeed, next to requirement specifications of the new technology, we need to be able to confirm that we actually met the requirements. So the testing is a very important factor. So thank you for this remark. Let me go. There is not a lot of people working on quantum communication. There was someone here. Yes. I'm going to ask you a question which is related to this. It's about standardization. What is required to be able to set up such an infrastructure that we actually have with the EU situation of having multiple countries, 10 of them now being able to connect or wanting to connect to each other, to let them communicate?
So I'm Florian Frövis from ID Quantique. Standardization, yes, I mean there are a lot of efforts currently. There are even maybe too many efforts because there are different organizations like ETSI, ITUT, and others like ISO, they're also thinking about this. I mean, one critical thing about standards in QKD is the interface between the QKD devices and the encryptors, the classical encryptors we have on top of QKD. Because if you have a real large-scale network, you probably don't have just a single vendor, but you have many, and therefore the operator of the network has to also connect the systems of different vendors, and also this with the encryptors, with the classical encryptors. And yeah, for this we need standards. And at ETSI there are also like 2 standards that are currently discussed, which doesn't help because yeah, now there are like 2 groups of yeah, organizations, academic and industrial, that follows this. But I think it's also related to the remark of Andreas that not all details are clear. In particular, the design of the network, for example, Deutsche Telekom, their ideas looks different than what we see, for example, in Korea or Telefonica in Spain. And this would influence, or this influences a lot the standard, because the design of the network determines the functionality and also the interfaces. So it's, I mean, also coming back to the other question, I think the core technology is more or less ready. I mean, as Rob said, you can always improve, but I would say the hardware is there. The question of the fibers is open. I think, yeah, I mean, the cost of ownership of having a dark fiber network spanning whole Europe, this is not negligible, but also there is, yeah, it's also not trivial to integrate QKD into existing or on fiber networks that have classical traffic. But this is really fundamental on the physical level. You know, you cannot just put a weak quantum signal next to many other classical channels. So, yeah. Okay, I spoke a lot. Thanks.
Yeah. No, but I still have one question for you. As having already a commercial product, can you think of what will be the use of this future quantum communication infrastructure network in Europe? Can you maybe think of, based on your current customer base and users, what would be the users of the future network?
Are you talking about the use cases, or?
No, or users, or yeah, general, and the users or use cases.
There are a lot of use cases, and I think this is also evolving. I'll just give you one example. From CERN, we know that they develop also on ideas of, okay, maybe it doesn't matter if it's CERN or not, but with, for example, artificial intelligence and large computational power, there is new protocols, new algorithms that process medical data, so data from patients, which is typically not done in-house of the hospital. So this is a use case that appeared like recently. So 20 years ago, maybe people didn't care too much about this problem, but nowadays it becomes real. Also 5G, and yeah, there are a lot of uses. Yes.
Thank you very much. Okay, yes, sorry.
Thank you. I'm Tony Apollago from Malta, and I wanted to comment on a few things that I heard from our Swedish colleague and from Midi Quantique about the network. So if one is to use the network for data transmission already existing, so put in classical networks, quantum signals, and Malta is amongst the countries that signed the QCI because it's very interesting. I see it's strategic for Malta, being small and isolated. It will be to have good quantum connections with the world. And there has been an experiment in Malta using the cable between Italy and Malta to send polarized entanglement photons. So there is something. But the cable was owned by a company, Melita, and then you need to connect to another company. So the question is, in the EuroQCI initiative, is there a table of the different stakeholders that country-wise have the network? Because one has, it is related to standardization as well, probably. Thank you.
Yeah, very good point. Thank you. Let me see. I'm going to close this discussion about this, and here, can the mic of David react on it a bit? I'm not sure.
Answering your question, yeah, okay. Answering your question, the study that is going to be conducted about the architecture, the idea is that the different member states within the initiative, they will nominate a technical contact for each of the countries, and this person will be the responsible to actually feed the different use cases to the company or consortium of companies that will be actually conducting the study. So I would say that would be the connection between the real use cases and the study. So it's good for you to know that, that if your country is in there, there will be such a person acting as an interlocutor between the use cases and the study.
Thank you, David. Thank you for the input for the quantum communication infrastructure. Next topic is presented by Torsten. It's about the ambition, which is maybe less pronounced in the discussion so far, about having a quantum computing infrastructure in Europe. Please, Torsten.
Okay, yeah. Thank you for giving me the opportunity to pitch here some questions. My name is Torsten Last from QTech, and what I also want to stress, I'm a senior system engineer in QTech. This is a kind of position or role which hasn't existed until recently in this kind of framework of quantum and information sciences. So I'm working always, or trying to work at the interface between technology development and research. And this quantum computing infrastructure question then leads to a very strong or interesting pathway towards. And when I stress infrastructure, I pretty much also want to ask the community, whether we need, for instance, also an infrastructure roadmap. 3 questions which will guide these pitches and hopefully the discussions are: why do we need, and who will use, and what you want to do with European-wide quantum computing infrastructure, and I also would like to extend it to a roadmap. To set the stage a little bit also differently here is Moore's Law is and will be a great success in the computational area, and what helped us a lot in the decades past was the Itrs Roadmap, where lots of different things, computation were discussed, device design technologies, I only named tunnel FETs, spintronic applications. So we were organized and were able to find step by step the pathway to more and more advanced technology nodes. Currently we at technology node 10 nanometer, and we even will proceed towards 3 in the next decade to come. It was always an economical law, this Moore's Law, and not necessarily a fundamental research or discovery law. It always involved also monetary considerations, so that progressing is also feasible budget-wise. So here the quantum computing paradigm currently is a good new perspective, but what I want to also stress, this is one of many different opportunities for the future. And it's very important to work out right now what exactly is the place of quantum computing in this, let's say, environment of opportunities. Others would be kind of more related to neuromorphic computation and so on and so forth. So it's very important to find out what business model lies behind our quantum computation efforts. And here now, next to the initial questions, I will give quite a few other questions to the audience, which hopefully also help start this conversation. One of them would be, how can we make sure that quantum computing becomes economically viable part of this computing ecosystem? Do we need an innovation roadmap? So I will repeat myself. If yes, what should actually be included? And how do we should organize that? The other part is then, if we agree to that with a yes or no, with a yes answer, what would you see as important factors for the next 5 to 10 years in this kind of infrastructure and supply chain roadmaps or priorities? What I mean by infrastructure, it is mainly hardware at this point in time. What I want to stress, we really have to build the hardware of the quantum computer on which we can then put the software stack on top of it. There are initiatives going on in US, Europe, and worldwide, and it's by far not exhaustive, these pictures here. But what I learned also in this discussion here currently, that the goal in Europe is also to get a system up and running with 50 to 100 qubit entities. So this gives already us a guideline when we think about architecture. So as I said, my role is system engineer, and I want to bring system engineering to this community, like my colleagues as well at QTech. And it's also an interesting question to the scientific community. How do you see this kind of approach? It is slightly different from I heard this morning again, bottom up, quite a bit. That's important for the scientific community, but for certain aspects, a top-down approach might be required or might even be a better solution. So how do you view a system architectural approach? And yeah, it can help, of course. I'm a supporter of this, but I also would like to hear your feedback. I would say it would help the acceleration of certain technologies and would also better stress finding the gaps of innovation needed. Then the follow-up question would, of course, then right away be, how could you organize, or how could we organize in a decentralized way this quantum computing system engineering principles? We cannot go through the whole stack of the system, but I think let's go to the bottom of it. There is questions which naturally arise on each layer of the system. One would be, of course, at the bottom in the quantum plane, is there sufficient capacity available in Europe for manufacturing quantum processors? When I stress 50 to 100 qubits, you need a certain decent infrastructure of design, design rule way of working. So how people in the IC manufacturing life cycle actually establish certain ways. And what I picked up also in recent talks, yes, indeed, Europe has a number of nanofab facilities and RTOs, and we will hear about that. But how do you personally see that when the quantum plane is an important factor? How do you see actually the lack of high-end advanced technology node, high-volume IC manufacturers here in Europe, who have really strict guidelines and know how an IC circuit should work and should be built? Let's assume we kind of approach the solution to this system. We built a quantum computer. Then we can also ask ourselves, let's deploy or think about a quantum computing infrastructure, and how could it look like? And one idea would be, of course, to have a decentralized network, like opening access to many different hardware and software solutions across Europe, with an organizing umbrella or hub, which then can give access to high performance computing, the quantum computing systems, even to quantum testbed facilities. Concluding, I would like to also find, I want to build the system, but actually what are we going to do with it? Is it fully basic research? Is it fully educational? Or will it be also leading to really kind of innovations and some new findings in our field? And so I would like to take over to hand over to Harold. Thank you.
Thank you, Torsten, for this introduction. Yes, already, that's what I like.
All right, just to disclose my interest, I'm Mikko Möttönen, I work for Aalto University and VTT, and I'm also founder of IQM. In my opinion, for the first question, I think we definitely need the quantum computer infrastructure, because now we've seen that in the Flagship we have several programs. One of the is Open SuperQ that is developing the 50 to 100 qubit machine, and we need the infrastructure basically to boost this sort of effort into the industry, so that the industry can pick up on the Flagship, and basically that way Europe can capitalize the European knowledge. That is a great way to start, and I think then we can scale up from there. There are many other institutes around the world who are interested in these kind of machines. For the scientist, it may seem like that, you know, who wants, I mean, you cannot, there's no quantum advantage in these machines, as we know. But nevertheless, there is interest. And I think if we want to start the quantum computer industry here in Europe, that's absolutely necessary.
You state there's interest, and no, you're not ready yet. There is interest, but could you tell something about what kind of interest? Is it from the education and teaching perspective? Is it interest from, what kind of interest is there in this infrastructure?
Well, I think these institutes, they are looking at on the largest perspective. So this is a technology that still, of course, to get quantum advantage requires many years of development. But it will not happen unless we start it, and we have to start it now, because we know that elsewhere in the world it has already been started. And we really have to start now the commercial building of quantum computers in Europe. And it is, as you said, part of it is maybe educational, but it's also preparation for the next generations of machines that can actually bring us the advantage.
Thank you. Yes, Frank, Willem. Yeah, go. Whoa, no, there's a lady just going for you.
Thank you. Sorry, yes. As much as I pretend otherwise, I'm a theorist, which you have just seen. I've already introduced myself before with my affiliation, but now I should also introduce myself as the coordinator of Open SuperQ. And I think one discussion, there's kind of two things that I want to bring up related to the discussion. One is, I think we have been working so much bottom up because we were honest and cautious. We have seen in the superconducting qubits community, I think many people did not want to make the same promises that the SFQ community has done, say in the late 1980s, which ultimately have not led to the 700 gigahertz superconducting processor. And I'm still wary when people tell me how great their system is acting in a big stack, when on the other side they have crappy qubits. I mean, we need the full stack thinking, but without good qubits, nothing works. The second food for thought I would like to bring in, we often hear, and specifically in Germany we hear, that people expect that quantum bits get commodified soon, or in foreseeable time, the same way, or quantum hardware gets commodified soon in the same way as classical hardware has done, in the sense that it will be cheap and we will all buy billions of it. And I don't know whether this is ever going to happen, but we need to make sure that we are not getting into discussions where we're saying, oh, we don't need hardware in Europe, we just need software. Let's keep in mind that even though, you know, classical bits and bytes we can buy very cheaply from Taiwan, we're not doing the same with, for example, cars. And even if, you know, we should probably also not downplay this in the opposite direction and say that there's only a world market for 5 quantum computers. It's probably a bit bigger. But even if it is still the case that we have a few quantum computers in supercomputing centers, which ultimately will have error correction. Quantum computing will still be useful even if, you know, the hardware is not going to become cheap. These two discussions I wanted to throw into a further train of thought.
Thank you. There's already someone who wants to respond to that.
Hello? Yeah, here we go. So Simon again, this time the light's not going out, so that's good. So I think this is a really interesting one. There's kind of a problem which we don't talk about very much, but which has become very apparent in the UK as we recently renewed the hub structure on the quantum computing side. There are a lot of different approaches, and I don't think it's possible to compete with the likes of Google, who have selected one credible approach and are just pumping loads of resources into it, by continuing to spread resources very evenly over a bunch of different ideas. That's an academic way to just explore interesting physics, but it's probably not a way to deliver a technology. I don't have a solution to that, but I do think it's a real challenge. If you gave me €1 billion and said, compete with Google, I would not spread it 6 ways and spread it over a whole bunch of different ideas. And so I don't know the answer to that, but I think it's a real issue.
But I'm not really understanding. Is your opinion that we should compete with Google?
Well, I mean, that's what we were hearing a lot about yesterday, right? I mean, if you want, I mean, not specifically Google, if you want in Europe to have machines that pass quantum supremacy and then deliver quantum advantage and so on, there's no point in doing that 10 years later than it has been achieved somewhere else, right? Because the industry will exist somewhere else. And so you must compete on some level. You don't have to make your whole story about compete with Google, but implicitly it's required. And I don't think you can do that by spreading resources in a sort of equitable way over every different angle.
Okay.
Just briefly, the different approaches to quantum computing historically come from physics labs. Everybody who runs a lab says, oh, this is a cool thing. Maybe my approach can be a quantum computer, and that's great. But at some point, you have to narrow the field.
Yes, I think it's exactly what we're trying to make clear here. Before you're going to respond, Frank, I'm curious, how many people are active on technology development, quantum technology development relevant for this topic? So who's actually working on either software, hardware, the full stack approach, so the devices, the control hardware, the software, who is working on it? Please raise your hand. Thank you. I'm a bit surprised. Everyone else is working on sensing and metrology? Okay, let me just test. Who is working on technology for sensing and metrology? Yes, and then finally, who is working on the basic science and the physics and the academic? Okay, well, that's, for me, a bit surprising, but it's good to see that. Nick, could you take note a bit? Yes, thank you. You were heavily nodding about the remarks just being made, so maybe you can share your thoughts.
My name is Göran Vendin Chalmers. I'm working on the Open SuperQ together with Frank Wilhelm and a lot of other people. And the question is not really to compete with Google. We just have to do the same. I mean, 10 years ago, we and John Martinez at Google and so on, Google didn't exist in this sense then. So we just been working together. Now, John Martinez's whole group was actually bought by Google, and they get fantastic opportunities to go of critical mass, and that's what we have to do also. We have no intention to actually abandon the kind of approaches on superconducting quantum computing that we are doing. Of course, there must be other ways, like ion traps, maybe optical, and so on and so forth, but we just have to put enough resources here, and we have this Open SuperQ project that is going to try to compete with Google in a few years, right? The important thing for Europe is that we don't, in the upcoming new session of the Flagship, we have to go this way and actually just put more efforts into these things. They already exist.
Okay, thank you. I think one of the key things of Google is that they selected one specific case, and therefore they could deduce the requirement specifications of what their stack would need, and then they could full-fledged, dedicatedly develop the hardware needed to achieve their goals. So I think that's some take-home message here, that we have to select something that we want to pursue. And now I'm going to ask Thierry. I'm going to ask you a question, the last question. What if a quantum computing infrastructure would be available? What would you do with it?
Well, it's a difficult question because I'm not involved in quantum. Oh, okay, sorry. So I'm Thierry de Bucher. I'm chair of the SEB, sorry, and also coordinator of a project Asterix, which is dealing with quantum sensors, so very far away from quantum computing and quantum computing infrastructure. Well, this is the question about the use case. And, well, I have no real idea of what to do with a quantum computing infrastructure, but maybe we could identify some useful questions for applications. For example, optimization problems, which are very common in industry, where you have to optimize big networks, for example. You need quantum computer. This could be an application.
Thank you. Let me see. Yes, Victor.
Hi, Victor Land from Qsoft in Amsterdam. I'm just wondering if people are getting worried about the lack of answers to now and in the previous discussion about what we want to do with it. I'm getting a little puzzled. You're not an expert on quantum computer, neither am I really, but no one really seems to have a clear answer or what we want to do about it. I could tell, well, we need use cases and we develop software and applications in Amsterdam, etc., but software is somehow excluded from this discussion, which I find strange from a systems engineering perspective even. But isn't that worrying? Are we doing this for technology push purposes only? Because that doesn't make sense to me.
But there are plenty of use cases. I mean, at least in the Open SuperQ project, we're bound to do a lot of elementary quantum chemistry, simulation, Coulomb, electron correlation problems, and so on. I mean, the problem is that they tend to be toy problems so far, right? But they are there all the time, so we sort of know exactly what we are doing.
Thank you. I'm looking for Diana from Work Package 3. Do you want to? I will get back to you. Something about use cases?
Yes, this is a great question, and we will have some workshops next year just to gather all stakeholders, industry and academia, to answer these big questions about use cases, and we hope we will improve on this matter soon.
Thank you. Well, I need help here. I will go to you.
With the danger of sounding too alarming, but we are trying to sell a €1 billion flagship to the European Commission, right? So I don't think we can answer those questions a year from now. That would be my opinion, humble. I'm not, you know, I'm still young in this field, but isn't that a little too late for all of you?
Thank you. Let's go to, yes, sir.
Hi, I'm Radu Nichoyu from the SAB. So I wouldn't worry much about the question of what to do with technology, because if we look in the past, I mean, there have been revolutionary technologies like the transistor, like the lasers, which at the point of invention, nobody knew what to do with them. What is a transistor good for, or what the lasers are good for? But once they've been there, people were building on that and they invented new uses of that. So I think it's a bit premature to answer that. So we just look at the past and it happened with the lasers and with transistors.
Thank you for that comment. Yes, no, yeah, sorry.
Hi, my name is Thomas Kopp. I'm coming from Luxembourg, from a European Trust Service provider. We are working on a QKD project, but to answer the question concerning use cases for quantum computers, there are lots of use cases. I would say all use cases that need computation power, the use cases we have today, like weather forecasts, like analysis of ADN, of human ADN, like analysis of pictures, of satellite pictures, and lots and lots. So everything what is calculated by computers of today, but with much more power. That's it.
Okay, and then my question is, because it's very low technical readiness level at this point in time. Oh, yes, okay. I will stop my comments because it's more interesting to see, ladies first, what other people are thinking.
Laure Lebas from SAP. I'm Research Project Director and taking care of a few projects in quantum computing. We do participate in Quantum Internet Alliance as well. My point, I'm trying to look also beyond research. At some point, if we have the use cases, and we do have already some idea of what could it be, optimization and machine learning, for our software that our customers are using, so they probably will have, they will continue what they do today with classical, and at some point they need to call some quantum routine. So there will be a need for an industrial cloud and services, and I mean central quantum computer that we call from time to time, and that should be transparent. I mean, the customer doesn't need to know that, okay, this time is running on quantum, etc. So we have to prepare. I mean, this quantum computing infrastructure could be, a pilot for this future quantum architecture that we want to build. I mean, that's what we should not lose. I know it's like 20 years, but.
Thank you, thank you. 1 sec. This person was Philippe.
Yes, I would like to add one idea to what we're discussing. I think I'm Philippe Chomaz from CA and in QFlag organization. I think it's also a way to create a market. If we look at what US is doing, US is giving money to DOE, Department of Energy, in order to buy quantum computers to start to do something. The performances are not yet at the level we want, so maybe we start with toy models. We compute, they have computed the deuteron, which is something you can do at elementary school almost. But in fact, we create an internal market for our startups, and we start to create also an ecosystem. So it's not only to show our muscles, it's not only to start to run to be in the race, it's not only to educate people and to start to create a community. I think it's also a way to create a market, but of course it's not a mass market, it's an internal market. It's triggered by government, but this is a way to finance startups, and I think it's the first market they can access now, so they may have revenues and they start to be in the race themselves.
Thank you. There was someone here. Oh, yeah, but there was another person here, yeah.
As far as the quantum computing goes, I think one of the main applications would be the crypto analysis, I guess. Nobody wants to talk about that, but the main motivation of this quantum computing is, I think, the crypto analysis.
That's a good point. So crypto analysis is one of the first big applications.
Aye, now that theory kind of came back to my initial point, I couldn't more agree. That was said in another words that I wanted to say early on. However, I would like to now come back. You had one question on the slides that can Europe actually, is there capabilities in Europe to make quantum processors? And that is excellent question, because we have to now think about exactly like the size of the market that we have now. It is tiny, obviously. And for this tiny market, I think we have perfect capabilities at the moment. Like, for example, even here in Finland, we have facilities that we could fabricate let's say, 100 quantum computers per year. And even the market is probably smaller at the moment. So, but if we really want to start to make millions, you know, that of course will be very, very far in the future. And for that we have still time. And once there is such a demand, I mean, then of course all these big foundries, they become available. Now the problem with the superconducting quantum processors, for example, is that there are lots of great clean rooms here, industrial clean rooms, even in Europe, in US, but they're making so much money that this small market is just not financially interesting for them.
Thank you. Last remark from William, and then we close the session. Before you...
the eyes of speaking twice, I'll do the same. So I have one remark on the cryptanalysis statement that was made. The German Information Security Institute has actually published a study how hard cryptanalysis is, and it makes it much harder than, for example, chemistry applications that we currently anticipate. So the quantum computer that you need for cryptanalysis is unfortunately or fortunately much more demanding than the chemistry one. That just as an aside. But I wanted to answer to the discussion about competing with Google, and I wanted to answer to the discussion what we want from an infrastructure. I do not think that an infrastructure should be the competitor of Google. It should be an enabler for Europeans to pick this up. What I would want for an infrastructure is to give our research groups the opportunity to do things where the required scale is something they cannot achieve themselves. If somebody has a new method in quantum computing that they want to plug into a bigger system, if they have new tools that they want to connect to an existing system, I think this is something an infrastructure can do. A publicly funded infrastructure is not a company. And in the long run, this is probably also a healthy industrial perspective, because the Americans have a tendency to create large companies that make everything, ACME, the American company that makes everything, whereas as Europeans, we often embrace that a complex system consists of many, many contributions that then is integrated by somebody. The complex system that Rob Thew has shown was, I think, a Japanese motorcycle, other country, but I'm sure it has parts of 20 countries in them. And an infrastructure can, I think, foster an industry so European companies play a decisive role in building a quantum computer, no matter who puts the last sticker on it.
Yes, thank you. With that comment, I would like to end the session on the quantum infrastructures in Europe. We have discussed the why, but also what is required for that. We will now move on to the how. So the what we have been discussed, and the next session, the next hour will be about how. How are we going to indeed build this complex system with all the know-how available in Europe, and how are we going to create quantum devices. And therefore, I will hand over this session as moderator Rogier. He will introduce himself, and two more speakers will introduce the discussions.
Thank you, and thank you guys for the session of this last hour. Yeah, my name is Rogier. I don't even have a last name, so that's fine. It's a typical Dutch name, nobody cares. The innovation working group was there originally to, or it still is, to help bridging the gap between the academia and industry, for which we have set up different initiatives. One was about the accessibility of, for small companies especially, to Nano fabrication, also to reach out to professional organizations, both in the standardization, in the photonics, and all the other environments. But I think it's good to quote Tommaso of his closing remarks of yesterday afternoon, that some things develop quite fast. Sometimes it seems like we progress slowly, but a few things are developing fast. We see already that we're building systems, for which we have a discussion about system engineering approach. We come back to this later. But also the infrastructure is a large system. We have seen also, for example, in the national agenda in the Netherlands, that we should work harder on the higher technical education, because so far we tend to talk about academic research only, but there's clearly also higher and maybe even medium or lower level education needed. And you can place your remarks later on. Please feel free. But now first back to the, maybe I should talk for another 30 seconds. First back to one of the key challenges we started out with, how to create access to fabrication facilities, because it's an interesting debate with our different levels of quality, accessibility and price. And it's important for our field to have the access to the proper clean rooms. Yeah, are you good to go? Not to go? Because Michel knows a lot about it and would like to give a small overview of what he knows about this and the clean rooms we have in Europe and how to access them. And that was meant as a kickstart for the discussion, to hear from you what you need or what you need more.
Okay, while waiting for the slides, just first to introduce myself. I am Michel Abashiri. I'm working at CNRS in France, and I am coordinating a project with research infrastructures mainly for academic research. So I will try to talk about nanofabrication issues. Nanofabrication is something that is, for me, only a tool. But this tool is common to probably all fields of quantum technology. So the important thing is that we need to have a good toolbox to work. And to do that, I think that the first thing is to fight against fragmentation. The landscape is very fragmented in nanofabrication. So what we would like to do is to be able to fight against this fragmentation, to be able to make a more efficient use of the money that we get. Okay, so that is principally for basic research, but it's probable that some ideas that I will present can be also adapted to other kind of sectors, such as RTO development, etc., because the fragmentation is there. So the network is this Euro Nanolab network is a network of clean rooms. It's focused only on technology, not on projects. So it's really nanofabrication technology. It has 14 partners currently. Each partner is a country, but in a specific country, there can be several clean rooms. Something like, because there are already networks of clean rooms inside the countries. So for instance, you can see here that totally it's 40 clean rooms. So what is the kind of model that we promote for basic research, of course? It's inspired from the US model a long time ago, but we still are trying to develop that. So what we offer is a nanofabrication service in open access, mainly in self-service mode. It means that the user should go to the clean room to do the job, and we give them access to the equipment, training, and know-how. Of course, any kind of user is welcome. It can be academics, but also RTOs, industrials, and so on. The access conditions are quite clear. We accept users only on technical feasibility, so there's no selection of the processes of the projects. Sorry, to give access to a clean room. Of course, we have to have a user training, and of course also access fees. Then, to fight against fragmentation, we have tried to promote some ideas that are already shared by the clean rooms of the network. And the first thing is that we want to implement a highly integrated, coordinated infrastructure with a central hub. And the central hub will be responsible to pool resources. And something that we want to pool is the know-how. It means that we would like to share nanofabrication processes. And sharing nanofabrication processes has some good, of course, outcomes. And the second thing is to undertake joint activities together to harmonize procedure, to have access procedure that are well harmonized and more transparent to the user, depending on the place, and also develop jointly some new nanofabrication processes for the community. And so we see the added value in accelerating user research, because we could be able to provide to a user a process that does not exist in his favorite clean room, and that may exist and ready to use somewhere else in Europe. So that's the main important thing. And then we also want to target scientific community's requirement globally to know what they need and try to join efforts to cluster nanofabrication clean rooms to be able to address the challenges. So that's what we are trying to do with the quantum technology flagship community, because we think that this may be very useful. Then a side effect of this organization is that we would also like to have a very very efficient data policy management. In the long term, if we want to exchange processes, we will need to have a high degree of standardization of these processes. The process description should be highly standardized everywhere in Europe. And so that's why we're also working on this kind of issue. Okay, so what we did is to start working with quantum technology. For the first meeting of that kind was yesterday. We had a workshop to try to start identifying some interesting challenges. And well, of course, it's a first trial, and we didn't go into detail. I just picked up a few ideas that came out of this workshop about superconducting qubits. As you can see, now the target is making more than 50 entangled qubits, but the technology is quite mature to my understanding, of course. The main issues are maybe now on integration, using, for instance, flip chip technology or TSV that are shown here. And on silicon spin qubit, it's I would say more difficult from the technology point of view. It's less ambitious. 10 entangled silicon qubits would be very good. But there is a material challenge. First, the 28 silicon is really a must in this field, because the coherence time is much better. So there is another problem associated to that, is the supply chain, because it's difficult to get that, and I don't know if you are really self-reliant in Europe. But I think that it's a very strategic issue. Something should be done there. On the process point of view, there is a very difficult multi-layer integration challenge on this kind of qubit. And then we had also some discussion about photonic qubits, where there is also an integration challenge. And it was highlighted the importance of single photon laser sources. Anyway, now let me go to some open questions for a system of quantum device fabrication. What I would like to say is that what I presented is, of course, for basic research, but these kind of ideas may also apply for RTOs or whatever, even for industrials maybe. We know that quantum computing means new infrastructures and also new supply chains. So that's something very important. Of course, we have a lot of players in Europe, but well, what is the case in academic research, and should be also the case elsewhere, is redundancy between the activities of everybody. So everybody is reinventing the wheel, in its own infrastructure, and well, maybe we can try to avoid this waste of resources. So there's a discussion about general purpose platform, versus specialized platforms. The general purpose platforms is providing multi-technology to the users. The good thing is that the nanofabrication is possible on a very different topic, and flexibility is possible. Flexibility is the keyword for basic research, because we need to have an offer to a very wide diversity of questions from the users. But the problem for that is usually we have lower quality and reproducibility because many different users are using the same tool, so there are some interactions. The second possibility is to have specialized platforms, but of course you will solve a lot of problems concerning technical reliability and so on. But of course, it will be globally more expensive because you will have only a limited number of users on your tools, and of course, it's certainly more true for academic research. But you will put more money probably for a result that is not so global. Then. My last slide, I will stop on that. The question is also about the open platforms versus closed platforms, because in the open platforms, as I showed you for your NanoLab, external users have access to every platform. So this justifies maybe a larger investment on a variety of materials and tools, but possibly there could be less availability of time for some projects, and we have probably to face intellectual property concerns. In the case of closed platform, of course, in that case, it means that no user external user can access to the fabrication platform. So it means that there are, of course, less perturbation from external users. It's better to ensure the confidentiality of what's going on in the nanofabrication infrastructure. But of course, again, it's possibly more expensive. So the question of cost is always behind that. How can we optimize the system to be able to do more with the same money? The last issue that is shown here is standardization. I've shown you about your NanoLab and the reason why we do that. But this was designed for internal academic use. But as you know, of course, standardization is something that is very important also across the value chain, because you have to be able to transfer correctly every know-how, every tool through the value chain. So it's very important to try to standardize these questions with common databases, establishing standard processes, and so on. And also, this will give a possibility to replace failing nanofabrication provider, so to secure the supply chain. Okay, that's enough for questions.
Is this one? Yeah. Should be enough for a few questions. So some people are taking notes, so apparently there's some interest. Yeah.
I'm Daniel Estef from CA Saclay, and I would like to give maybe a slightly different view from what you say about the platforms. First, the last point, the standardization. Standardization is fine once you know the solutions. And the problem is that very honestly, we do not know the solutions. So let's go through the different qubits and let's finish by a comparison with a mechanical computer that Charles Babbage wanted to develop quite some time ago. So you say general purpose facilities versus specialized facilities. So let's start with the superconducting processes. The standard qubit nowadays is a transmon, which is just a single Cooper pair box in a very special regime. Up to now, no single Cooper per box has been fabricated in a general purpose large facility like that. Intel has been the only one large manufacturer able to make superconducting qubits. The other ones have always been fabricated in rather small facilities, mainly used by researchers. So here, if you make, say, a big infrastructure to develop that, this will be fine up indeed to about 100 qubits. But the problem is that you want to go to the next stage. If you want to really to develop a fault-tolerant architecture, you need to increase by the number of qubits by a very large number, and then it means that you need a much more compact qubit. It means that the superconducting qubit we have today is not compatible with large-scale integration. So which means back to basic research. Now you have mentioned the semiconductor qubit. The situation here is worse because the semiconducting qubit is not yet stabilized. So there are some, but they are totally non-scalable. So it's so you need definitively to make more research on that. So, and this research has to be done in very close collaboration with an RTO because you do not make semiconducting qubits in your small lab clean room. No way. Then for photonics, for many platforms are able to integrate photonics, but not to make the photonic sources. Photonic sources can only be made in really quite advanced semiconducting facilities. And as I said, last but not least, some time ago, Charles Babbage had a design for a mechanical processor. His design was correct. It proved to be operational, but a bit too late when it was recently made in UK. So what we think that maybe today we do not have the good qubit for really making a quantum processor. Maybe we are in the same situation. So it's very, very important to develop the qubits that have already demonstrated some success. But the real qubit that will make a quantum processor, maybe we don't have it. Maybe it has not yet been invented. So I think it's extremely important to think that we should, at the same time, develop the strategies that have demonstrated some success, but you should not close research in the lab. That would be totally detrimental. And be sure that even in the US, they do that by both by developing, say, big, companies that develop big projects, but at the same time, many university labs that still develop tomorrow's qubit because we need it.
Yeah, sure. You're off.
Okay. Oh, all right. I just want. I mostly agree with what you said. I just wanted to clarify that standardization here is not standardization of quantum technology issues. It's standardization of nano fabrication issues. So it's very different. This enables to have communication and to be helped by other infrastructures. And it's especially useful for people in basic research because they always have some difficult problems and different problems. So finding something elsewhere is something that is very useful. But on the other statements, I would like to say again that this was designed for basic research and may not be applicable to more developed research.
Yeah, sure.
Yeah, and I think the idea in this Euro Nano Lab was not to actually establish a big facility that would do get users in and do fab, but it was to join the existing clean rooms, and that was, I think, a point here that we don't need. We are not trying to build a dedicated clean room for certain technology here now. And I think that is most likely at least from the scientific point of view, that is too early. So about this general purpose dedicated, I think it's good that we have many general purpose clean rooms where we can do superconducting chips, or we can do silicon quantum dots, or photonics. That is absolutely necessary. But I think at some point, if some of these technologies becomes more industrial and we see that, okay, we need to fabricate these more and more, then I think we definitely start to need also dedicated clean rooms for that particular technology, because what you said, that the quality will be better, and if we want to build the best quantum computers, then we need good quality. Quality is everything in there. So.
Thank you. Are there other SMEs or other smaller companies with certain requirements or support they need? Or maybe from the AMO community with your ions and atoms, and because so far we just listed a number of solid state devices. But yeah.
So I am Meri Helle from Summa Semiconductor startup company, but I have a background in quantum physics. I was working for low temperature laboratory here in Espoo. But we are currently using the Micronova clean rooms in our daily operations, and it is really absolutely necessary. If this infrastructure wouldn't exist, we couldn't do anything here. And open access policy is very important. It's very important for the scientists, and it is also very important for the industry, because if you are developing the new technologies and new scientific or producing new scientific results, you need to fabricate the devices by yourself. You need to test new things, and you have to be hands-on. So, and I think this is a really great idea to join the forces within the existing infrastructures in Europe, because it's really about testing and writing down the processes carefully and then sharing the information. And it is typically very much that you need to be there, you need to look with the microscope, and you need to adjust the recipes. But writing down the instructions, how to do the manufacturing processes, and then sharing with the other facilities, I think this is very important. But then I would also like to mention that semiconductor manufacturing tools or nanofabrication tools, they are very tool specific. Even if you think that you have two identical tools in different locations, it's not just that you write the instructions and then press the button, but you need to do a lot of adjustments, and therefore you need great engineers and scientists to really fine-tune to enable high-quality manufacturing processes that will then enable the quantum devices, high-quality operations. Oh, thank you.
Thank you. Maybe a short response, and then we move on. Yeah.
Yeah, I just wanted to add a little bit on Mary's points that is, you know, when you do top quality nanofab, it's, you know, it's really like you do the recipe, and it's somehow with some magic and some attachments you've done along the years, it works. And then you have a huge barrier to take that to another clean room, or even one step of that to another clean room. Then that kind of decreases the motivation for people to actually to use this network, right? So everything has to be very well set up and tested that they can do it. And still, I think most likely still a huge majority of the users are actually local users, because it's just so expensive to send your best fab guy to France from here, and he might need to spend there half a year to get the process working. That's the reality. It's not just a single go, but to do that, it is a big barrier. So to decrease or to make the network actually to operate better, I think we should also pick on the idea that actually was in the last slide of Antti Vasara yesterday. What there was the last point was that, for example, VTT, he was saying that VTT is interested in operating as a foundry, so not only to allowing the users to access the clean room, but actually they have permanent clean room engineers who can do the processing. So if you submit your design and the process flow, the engineers could do the fabrication for you, and this would be, in many cases, much cheaper. And therefore, it would enable the more usage of the clean room network.
I would like to just comment on the last statements. First of all, for the portability of processes, we are completely aware of that, and there is a long-term project on this issue. This long-term project is a database project. It means that we have really to be able to know how to describe the process with all the details. Of course, presently we are not able to do that. Second thing about what you said is that in fact, the foundry is okay. The foundries are designed for specific kind of process. Problem of academic users is they never fit in this specific process. So they have to find somewhere else the necessary resources. So that's typically academic. Of course, for more focused nanofabrication facilities, it may be very different. That's all.
Okay, thank you for this moment. You're still around, of course, and people, please speak up, because Michel's a busy man. If you don't speak up, he's not working for you. Eh? There are more communities you can serve, also the photonics and the other groups. I invite now Emanuele to shed a different light on this challenge, more from the system engineering point of view, the approach that also common in industry, and we thought it's important to stress this, as it is also a way to bring the research and industry community together, because you need a common language before you can work together. There it is, Emanuele.
Yeah. So, welcome. My name is Emanuele Ceri. I'm a senior scientist at TNO, and I've been asked to briefly describe a system engineering approach which is slightly different from the most common scientific approach in order to develop quantum technology. As we heard in these 2 days, that is the must that we have to do with this quantum flagship. So just briefly, a sort of primer about system engineering and how does it work. So system engineering is an interdisciplinary field of engineering and engineering management that focuses on how to design and manage complex systems. And in this way, the individual outcome of such an effort, which is indeed an engineered system, can be defined as the combination of the components that work in a synergetic way to completely perform a useful function. So we start by defining the function that we want to achieve, for example, with a quantum computer. And we need to go through the full, to define the system that can achieve this function. What it means that we start by defining requirements. And what is plotted on the right side is this wedge model. It's implied that we started to having a system, and before starting to work on it, we have to subdivide it in the different subsystem and components, and to define each requirement that can withstand with both the full system picture and the different subsystem. So there is no requirement if we do not have a way to verify the system. When we have we have divided the system in the different subcomponents, we can start to work on it and start to build it up and to verify step by step the different requirements that we have achieved. Why is it powerful, this approach, instead of starting in a bottom-up approach? is because already at the requirements, level definition, and the designing of the architecture, we can consider also budget consideration and constraint. Looking now, for example, at the current trend, in order to achieve 50 to 100 qubit quantum computer with probably a limited performance from this kind of machine, we can already think that the different components that are existing now in the market, how expensive they are, and if the system that we can build it up is really reliable. So after that, we went through the system requirement review. One have to start to think at the different materials, assembly and integration phase, and start to look up how it is operational. What it means, just try to give an example. In Delft, in QTech, in collaboration between the TNO and Delft, we started 2 years ago to start thinking at the full system quantum computer. In this way, we start from the system architecture, and the system architecture is a comprehensive of different subsystems, like the quantum plane, where we have the quantum chip, but also we need this to communicate with the different hardware components around it, and at the end also with the software, so in order to be used by the end user. By using this system engineering approach, we were able to build up a roadmap and verifying step by step different milestones to be achieved. So we started with the system architecture, then there was a software, then already the first hardware, cryogenic hardware, and then we start to integrate the first devices and we can measure and calibrate. Now, what it brings this to us, this way of working, is that we have to answer the question, why at the moment, why today we cannot have a fully fledged quantum computer. So what are the challenges? So despite the fact that at the basic research, we still have plenty of very interesting challenging for every new sample that we're going to measure, and that we do not want to stop this interest for the scientific community. There are a lot of engineering challenges that pop up by building up this technology. Here we just listed few. It's not exhaustive, of course, but it's just to start the discussion with you guys. So from the quantum device manufacturing, it was already briefly described from more the academic approach by Michel, but still, qubit device present what we call different personalities. It means that in the different batch of qubits, we have a different response and different specification. This is a challenge. We still do not have any performance of record available for any qubit technology. We have challenging about wiring up of qubits. Now, starting from the fact that we have a qubit or a quantum plane with a limited number of qubits, if we have each qubits require signal in and out, and at the moment we have, it's hard to think of the architecture how to scale up the system. As well as the cryogenic environment presents challenging with respect to the power management. We have plenty of lining cable coming down to a low temperature environment, and this present issues from the power management as well as from the volume scalability. Within a fridge, how many qubits we can store. Or another challenge concerns more the scalable control circuits and the electronics around. At the moment, we still suffer from not having a dedicated or an ad hoc supply chain in the market for electronics for the quantum technology we're going to develop. And at the moment, we're using, let's say, bulky and expensive electronics equipment from other markets, and this is not a favorable or long-standing solution. As well as on the architecture, we show beyond an example of it, but it still is a preliminary architecture and is still confined at the 2 level of instruction. Now, to try to make more example, to concretize it, I like to use the example of QTech, of the quantum-inspired developer QTech. We start from the quantum plane. We have a silicon, we have a qubits device This needs to be interconnected with different hardware components to generate the microwave pulses to have these equals in and out. And then at the end, it has to communicate with the software so that in the cloud, user can operate it. And this has been developed so that different backend can be integrated, so not only silicon-based quantum qubits, but also other technology. So what are the challenges? Yeah, when we talk about quantum device manufacturing, currently we're going through a circle of design, manufacturing, and characterization calibration. This is currently present limitation, as mentioned, so POR is not well established for any technology, and this closed loop has to be moved to, it needs to get continuous improvement. Other challenging that we've seen is, for example, on the wiring up of quantum information processor. Yeah, if we compare today IC processor with, for example, the example over here, we see that there is quite a huge discrepancies in the number of qubits or transistor, as well as the pins that are needed at the end to make the final connection with the outside world of the device. Other issues concern, for example, the cryogenic environment, looking at how many, again, the number of wiring that we can put in the fridge is limiting the scalability of the system. Or as well, control and hardware and firmware that we are using is still bulky and expensive. Let's assume that we are using for microwave pulse without equipment that are in the 100K range. If we want to use each single qubit and we want to scale up, you can imagine that is not that affordable. So these were examples. Now I would like to start the discussion, to let them driven by Hiro here. We'd like to ask you how this quantum technology innovation roadmap can be useful in order to help to build up the EU quantum technology infrastructure we just discussed also the hour before. And topics that we would like to address where is need a subtopic of a system engineering approach is about requirement specification shall be this addressed in the quantum technology innovation roadmap can be addressed together. Standardization or supply chain development standardization, looking at, for example, the different startups that are luckily developing in different labs inside broad Europe, how we can generate and support the standardizing of this new equipment and tool. Or the last question is about how we can achieve a robust quantum device manufacturing platform. And I would like just also to give a slightly different accent from the talk by Michel, because from one side, it's clear that we have in Europe a world-class nanofab infrastructure as well as expertise. We would like to benefit and to maximize from that. The question is how we can use it at the best. Shall we, maybe it's just a repetition of some question, but the accent can be different. Shall we perform or pursue standardizing process and sample among lab? It was mentioned just the last question and comment was about having, it's hard to send a user to a lab in France and spend in a short time, or he needs to spend a long time to get the learning of that tool and infrastructure, but maybe there could be an exchange of sample among labs. And this would require, it would encourage some standardization. Or another question is about if, in order to boost this quantum device manufacturing, shall we push the existing nanofab consortia like ENL, the Euro Nano Lab Consortia, towards more IRTRL research, or shall we develop ad hoc equipment as well as ad hoc nanofab infrastructure? So with this, I leave the word to Rocky.
Yeah, thank you. It's good to make this example because it is the way to build really complex systems. If you want to have a car or an aircraft, this is the way to do this work, or a variation of this. It's not so well known in basic research because in basic research this model doesn't work. And these days we're talking about 50 to 100 qubits, which is somewhere in between, and that makes it really challenging these days to figure out what is the best approach. There's some personal preferences. But if you talk to industrial companies that you would like to partner up with, I think it's relevant to understand this language at least and see how it can help you and bring the parties together. Any reactions to this? Is this, yeah, Frank? You have 2 microphones. We can hear you even better.
So then you have to listen to me even more. So thanks, this was a great presentation, because in Open SuperQ, where we're hitting 100 qubits, we have the exact same problems. And I would also think that in the last few flagship meetings we had, the engineering discussions were the most complicated and the most frustrating, because it's just such a big animal to tackle. That being said, I mean, first of all, as a fundamental researcher, this plan and this cycle, how you engineer a complex system, reminds me of the plan for a PhD thesis, which is never how the PhD thesis turns out. And maybe one suggestion to make progress, because, for example, standardizing process and sample among labs, I can give you a 20-page document that talks about this. It's the interface specifications of Open SuperQ, where we make sure that a substrate grown in Finland with qubits made in Sweden fits into a sample holder made in Switzerland, and many other things. And so the point I wanted to make, it's more a statement than a question, you know me already, is that I'm in tackling the big monster, the big challenge, the big mountain of quantum engineering, I am missing one voice, which is the starting point set by the currently funded projects. I don't know how many fellow project coordinators of Flagship qubits are actually in the room. That's probably part of the problem. However, I would hope that the coordination action welcomes, and I would hope that the Science and Engineering Board actually does write down kind of a list of things, current engineering challenges bottom up, that we can connect to this process to actually have one starting point to supplement top-down discussions that also have to happen. And I would kind of like to call on the coordinators, most of the absent ones, to actually write something like this in the SEB. And I wonder what your reaction to this is, because you are, unlike me, obviously a professional engineer.
The ambiguity of this kind of approaches, yeah?
In the first slide, we show here the roadmap that we have designed, and maybe different from the example that you mentioned about the planning of a PhD thesis. We have managed to build up this roadmap in such a way that milestone was possible to achieve, actually according also with the time schedule. I do think that the approach here from the system engineering, as also mentioned by Rohir, that is the normal language standard, also by building a large technology with industrial partner, as the potential that you start to first decompose the structure that you want to build up, the technology that you want to build up, try to see the different aspects and try to correlate one to the others up front. So try to be more ready in order not to discover on the step-by-step that what you have spent months in here to develop at the end is not working because you didn't think properly up front. So I do think that this way of approach, more let's say top-down approach, is useful if you want to build up such a complex structures.
Thank you. Yeah, please.
Thank you. Maija Ojanen-Saloranta from VTT, and actually my background is in metrology, which was mentioned yesterday as this metrology community could help in these standardization issues, but also especially here when it comes to manufacturing and samples among labs. So maybe this nano metrology, nano manufacturing metrology community could help we here and provide help to develop tools for standardization and for reference samples and so on. So let's try to join forces here.
Thank you for this addition. Yeah. And we know that the metrology institutes have been working on a proposal, of course, to become active in this quantum domain. Ivo, you and your whole consortium are working on this. Very good. Looking at the clock, we also almost have to close for lunch, nearly. Yeah. So maybe some final remarks. The innovation work group and the other colleagues are trying to help you bridge between academia and industry, amongst other activities. Other suggestions or requests where you would like to see us to help this community? Maybe broader than just what we presented here. Could be also anything else. Please note that we're working on standardization these days. That's a topic that pops up, and that comes to the standardization from your point of view in the metrology domain. It is about interoperability, more in the quantum communication domain, but it can also be in the clean room facilities. It all sounds slightly different, but it is all under the umbrella of standardization, on what we will focus a bit more in the coming period. No further requests. Okay. We're done. We did our job.
In time. So I would say a round of applause to all the people involved here. They've done a great job. And also thank you very much for your contribution and for this lively discussion we had. So we now break up for lunch, and at 1 o'clock please come back and we will go on with the event. 2 o'clock, sorry.